Hi, this module is kind of different. We are trying to see how we formulate problems, not not solve, but simply formulate. Okay, and we'll try to do this problem 303. Okay, so again, we can think of the same three steps: defining, generating, and implementing solutions. You will see that most of these we skip because we're not going to actually solve the problem. We can still go through these steps just to be in the same sequence as others, and we can do a few of these. So for example, what are we solving for? So let's look at what are we trying to find here. It is the temperature in the tissue, in the arm, as function of position and time. So that's something we now know. Now you see the difference. Normally schematic is given to you, but here the schematic is not given. Because we are trying to formulate the problem. We are trying to start from the real thing, the actual thing, and then come to a schematic. So the schematic is not given here. Assumptions are not given here. So we can make some of those assumptions. So for example, so now to try to formulate, we are actually making these assumptions, which is not what you would do in most problems. You're not free to make these assumptions, but here the goal is to actually make these assumptions so we can come up with a solvable problem. Um, so the first thing we can do is we say it is symmetric. That will make our life easier. Then the next one is the boundary condition related. So ice pack maintains a constant temperature that does not change with time for the duration we are interested in. What will that do? That will maintain a constant temperature on the skin over time and make our life a lot easier to solve. Um, so the other one is ice pack length along the arm. This is long. This is long. So long that we can assume that the heat transfer is only in the radial direction. So no heat transfer along the along axis. So as we assume this to be a symmetric one, we're kind of looking like a cylinder here. Um, and let's see the next assumption. So the blood flow effect, as we know, is assumed uniform throughout the tissue. So it's not we have more blood flow somewhere and less in another place. That will make our life difficult. Um, so the properties of tissue are uniform all around. And so that also makes sense. Otherwise, the K, for example, is going to be different. And so solution is going to be difficult. So we are saying K is constant for this purpose. Okay, the second step, we basically have nothing because the second step is normally looking for what are the different ways to solve. We have not been asked to solve. So we do not need to solve. So this step is not needed for this problem. So the third one is implementing the chosen solution. Now again, we are not going to actually solve it. So we will just start with the detailed steps, and part of that would be to set up the governing equation, boundary condition, etc. So I want you to see this very important slide. What is problem formulation? So in problem formulation, we take something that is physical, that is a completely physical process, and write its mathematical description. So physical to mathematical. What is a mathematical description for this process? We need a schematic, we need a geometry, we need governing equation, we need boundary condition, and we need initial conditions. Notice all of these are equations. The physical part is gone. So physical part gets replaced by this equation. So the question you want to ask right away, and you should keep in mind that these equations better describe the physical process well, and there should be ways to check. So the way we check things is we come up with this equation, solve it, and then do experiments to then try to see whether we can match the measurements that we can make on a physical system. So again, problem formulation is replacing the physical with the mathematical. So as we start our problem formulation, the first thing we need to decide, what is my domain? Is the tissue the domain, or is the ice pack the domain? You know, as the tissue is cooling, the ice pack is warming. So are we doing the solution for ice pack? We just want to know how does it warm? Is that our question? So in this case, that is not the question. So it's how tissue cools. That is our question. So then the tissue is our domain. You notice that these kinds of things are, you know, trying to decide exactly what geometry I will use. It's not easy. So for most of the problems that you will do in this class and other junior level engineering science classes, this problem formulation has been done for you. The trouble is to decide on this geometry and see where we will have a simple analytical solutions that we'll be able to use. It actually requires first taking this class, meaning the things that we learn in this class will eventually help you to make decisions on what kind of a domain or what kind of other parts of problem formulation that we will use. So this exercise again is to see that part. We're not going to repeat this one, but we want you to go through this process. So the questions to ask to simplify the problem is, what is the boundary of the domain? So I already talked about, so in this case it's the tissue. Is there symmetry? So in this case, we are thinking that the geometry is symmetric. It's symmetric around. Is the physics also, so the geometry is symmetric, is the physics symmetric? Meaning, is there, let's say, more blood flow on one region on the upper side versus lower side? Then the physics is not the same all around. Then we cannot use symmetry. So everything has to be symmetric. For example, boundary condition. Is the temperature all around the same? Otherwise, it is not symmetric. Likewise, the initial condition. Before you place this pack, was the initial temperature uniform all around? Unless all of these are satisfied, we cannot say that there is symmetry. So for this problem, we're now going to assume that indeed these are true, and therefore we can treat the problem symmetric. The next step is the schematic. So because of this the symmetry, you understand that schematic is not given to us this time. But because we did all those discussion and made all the assumption, now we can draw the symmetry. So we said it is symmetric, so there is the line of symmetry, and then we have the bone here and muscle, and on this side of the muscle we have the cold pack, and so the cold pack would be maintaining some temperature of T cold, which doesn't have to be this. Um, it can be some other temperature, and we are saying T cold will remain the same. I can make different assumptions. I can say, like it was here on this slide before, that T cold will change. T cold will change with time. Why I crossed out that one is, for this case, if this temperature keeps changing, we will learn later on that the simple analytical solutions that we will use would not work. So you see how we are simplifying the problem for our purpose. We're simplifying in a way that we can solve using the tools that we would learn in this class. If we make this complicated like this one, yes, there are other tools used to solve this. They're not that complicated, but we don't cover that in this class because we want to learn the basic physics first. Okay, so next, after choosing the geometry, we come to choose the governing equation. Okay, so the governing equation, the first question is what coordinate system? Now we have three choices, three different equations that we either derived or discussed in class. And because this thing is axisymmetric, it is kind of obvious that it's the cylindrical geometry that is the most appropriate. Next, we need to decide which terms. So first is we want to do this as a transient problem. So this is my transient term, so we should keep that. Convection term has already been dropped for simplicity from these equations. So there, it is not even here. You see nothing with velocities in here. Then diffusion term or conduction term. Conduction term. So this is my conduction term. Notice that it has three terms because this is a general equation, so it has r terms, phi terms, and z. Now we said that this is symmetric. If it is symmetric, that means symmetry means temperature is not changing with phi, so that is written as del T del phi is equal to 0, then obviously del square T del phi square is also 0. Then we also said that it is kind of long in the z direction. What that means is things are not changing along this direction. We made this assumption. So this assumption means it's del T del z equal to 0. If del T del z equal to 0, then that also means del square T del z square equal to 0. Notice that I said flux equal to 0 here. Flux is what? Minus k del T del z. So in this direction, del t in this direction or in this direction, del t del z is 0, so the flux is 0. It actually doesn't matter how thick a region we choose because there's nothing happening in this direction. Everything is happening in the radial direction. So del square t del z square equal to 0 because del t del z is 0. So now we have this as my conduction term and then generation term. So generation term in this case is Q. Now this is sort of written in a generic way. So this same Q can include two things. One is metabolic and the other is blood flow. So we can include both of these in this Q term because Q simply stands for heat generation. So now we have a governing equation that has this term 1, 2, and the 3, those three terms. Now let's look at boundary conditions. So we have already discussed some of it. So the way you want to approach this, first of all, how many boundary conditions do I need? How many boundary? This is a good way to look at the problem. So we have these three terms, remember, in our equation. These have been dropped. So this is, of course, so this is a second order term. So when you integrate a second order term, you'll get two constants of integration that we need to evaluate, which means you need two boundary conditions. So it's second order in space, so we need two conditions in R. So we need a condition for R equal to 0, and that condition, because symmetry means del T del R is equal to 0. Things are symmetric with respect to T. Same T here as on the other side. That means del T del R is equal to 0. That's one condition. But because it's second order, I need a second condition. So here T at the surface is equal to some T of the cold pack. Okay, so now we got two conditions. Notice I don't care about any more boundary conditions because these terms have been dropped. It's first order in time, as you can see. So we need a condition in time which is called the initial condition. So the initial condition in this case could be simply T at time t equal to 0 is some constant temperature. So Ti is a constant initial temperature. Again, we are formulating these in a simple way. It doesn't always have to be constant, but if you don't make it constant, we cannot use the simple solutions that we'll derive in this class. Then, as we have learned, for boundary conditions, for second order, we need two conditions. For each conditions, we have these three choices. This is my type 1, type 2, and type 3. Temperature given, flux given, and convection. So in this case, this on this side, on the symmetry line, it is my type 2 boundary condition that we assume, and on this side it is my type 1. So we can use only two. We cannot use more boundary conditions for R. So the thing to remember is only one boundary condition at a boundary. You cannot have this and T equal to some value at this point. That is not allowed. Only one boundary condition. And then symmetry may not be provided to you. Symmetry may not be given to you explicitly. From the details of the problem, you should be able to guess whether the symmetry condition applies or not. So in summary then, we have a formulated problem. Remember, the physical problem was cold pack on cold pack over the arm. That was my physical problem. And this is my mathematical problem, all of these together. So they have three parts or several parts. Schematic, where we decide the geometry, governing equation, boundary condition, and initial condition. So this is called problem formulation, going from physical to math. And as I said, and I should remind you again, that this is what we are solving. We are solving this. There is no guarantee that when we have solved this, it is a good answer to the physical problem. We have to check, and often using experiment. The other thing I want you to see for the purpose of this class, that this is where we start to solve. This is where we start to solve. So quite often this will just simply be your first step, and then you'll go into details of how to solve this equation. Just for this chapter, just for this set of problem formulation, it's important that you know we are not asking you to solve this. We want you to stop at this stage. Okay? Thank you.